Uh, I guess I don't know what the official title of this one is, but anyhow, welcome to this introduction of Purdue programs. And so this particular section, I'll be talking about the additive manufacturing capabilities at Purdue. My name is Young-Shin. I'm a professor in the School of Mechanical Engineering, and I work on metal additive manufacturing. Also, I'm director of Center for Laser-Based Manufacturing. Okay, so with that brief introduction, let me get started. So probably most of you are already familiar with the metal additive manufacturing, or in general additive manufacturing. So I'll be talking mostly on the metal additive manufacturing, and later on, and I'll introduce some non-metal additive manufacturing as well. So there are many different types of additive manufacturing processes, particularly for metal, and you will see two predominantly used metal additive manufacturing processes. And one is called the powder bed fusion. So basically you pre-place the powder in the bed, and you basically scan this powder bed with a laser or electron beam, and actually you can create a very complex parts here. And you see a sample parts produced by this machine that the Purdue has there. And actually the geometry is kind of, you can achieve is mind-boggling. And so complex that you cannot actually build by any other manufacturing process. That's one of the advantages of this metal additive manufacturing process. Another one is here is a system also we have. It's called direct energy deposition. So the process works a little differently than this case. So in this case, a powder is injected into the laser spot. So basically, as a powder drops into the molten pool area, and laser will, the laser will basically melt the powder, and then as the laser moves away, and the molten material will actually solidify, forming basically 3D structures. So these are some of the examples that actually of the parts that we built in our lab. And the shapes of the parts you can build are less complex, but there are some other advantages, such as you being able to add a material to existing part, or you can actually create a functionally gradient materials, something like that one. Also, you can mix and match different powders. So there are advantages and disadvantages between, say, different additive manufacturing process. Anyhow, they work very similarly in basic principles. So where do you use this metal additive manufacturing? There are many applications you can find. And one is, as you know, you can actually build some parts and very quickly from a CAD drawing. So you can actually build very customized part. An example of such would be making implants for the humans. So ideally, you want to make an implant and matching the shape of a particular patient's bone shape. And exactly, the problem is that in the traditional way, they could not do this, so they actually make only 10 or 12 different shapes, and you have to put that in the body, and obviously it's not going to match perfectly. Now, with the metal additive manufacturing, and doctor scans someone's bone shape, and then you can actually fabricate the implant to the exact same shape of the patient needs. So basically, what we call is customized, mass customized part. Basically, you can produce parts as needed to the exact specification. Another application you'll find is actually what I call the hard facing. So a lot of metallic parts require some protective layers for wear resistance, corrosion resistance, erosion resistance, all kinds of things. So we typically use a paint to protect the surfaces, but you cannot use a paint for mechanically performing parts. So basically you apply coating, and that's what I mean by hard facing. So you can actually add hard abrasive, say wear resistant, corrosion resistant material on the surface, and using metal additive manufacturing, you can protect the surface and prolong the life of a product. Another area that is actually very important is that repair or remanufacturing. So, for example, if you think of an aircraft engine, and then while it's flying, and you can your engine blades can get damaged because a lot of foreign objects can fly into engine. You can get a chipping and cracks and things like that. And these are very, very expensive parts. So instead of making them from the scratch, you can actually quickly repair them and restore the shape. And that's another one. Another application is basically creating what we call the functionally gradient material. So in a sense, you gradually change the composition from one side to another side. So therefore, let's say you actually give a local property wherever it's needed, in a sense. And if you need higher toughness, you will actually use that material. If you need to have a wear-resistant property, then you're gonna actually add that material at outer surface. Or heat exchanger design is another good example. You want to have an insulated material and conductive material, and that way you can actually have a better efficiency in the heat exchanger. And without making really large, you can make it more compact, more high efficient. And also you can actually build a lot of new materials, such as a metal matrix composite, other types of new alloys. So this is a huge effort being undertaken in many say government agencies, because they like to come up with a new material. Metal manufacturing, actually additive manufacturing, is a good way of accomplishing a lot of these goals, because you can actually rapidly synthesize the materials in situ. And you probably have heard of something called the lattice structure. It's a topologically designed structure. So instead of you having dense structure, it's more like a mesh type structure. And once you actually build structures like that one using additive manufacturing, you can have something like acoustic optical metamaterials. These metamaterials don't exist in nature. However, you can actually build those things with very unique capabilities and the foam structures and things like that. And last one I talked about. So there are a lot of opportunities with additive manufacturing. Additive manufacturing process provide building very complex parts from the 3D drawing in one step. Okay, I also mentioned the opportunities for synthesizing novel materials, gradient structures that cannot be made by conventional processes, and also can impart the properties as needed. So therefore, you have a material part with many heterogeneous properties wherever it's needed, and the part will be simply going to be superior, and you cannot build the parts in any other way. And then also, additive manufacturing processes allow digital manufacturing on demand with the no inventory, right? So you can actually build the parts in Mars, in moons, and on ships. Whatever you need to build the parts, you can actually build the parts over there instead of making a parts in the factory, shipping it to other places. Okay. Also, additive manufacturing process can provide individually customized product. I mentioned that one. So a lot of people think this additive manufacturing brings new frontiers in manufacturing, and you probably know this one already. Okay, so by no means this list is exhaustive, but what I'm trying to show here is that we have done a lot of work on additive manufacturing, and this is simply some list of materials we have worked on over the years, and from steel, many other alloys and composite materials, and some other very exotic materials such as graphite, zirconium oxide, which are not easy to actually build using additive processes. So we have collectively a vast amount of experiences and knowledge in additive manufacturing here. So what are the research activities taking place here? I can divide the research areas in additive manufacturing into 3 groups. And one is actually predictive modeling. Okay, so one of the problems with the metal additive manufacturing is that there are so many variables. Some people say there are up to 102 primers. Some might say there are 41 primers. So what happens, there are so many primers affecting the final result. So if you have to figure out how to actually get the desired microstructure mechanical properties, and you can think of how many actually experiments you have to do. And so 41 primers, you have to do combinational and let's say experiments. There will be thousands of experiments you have to do. It's too expensive to do that one. So people are trying to do a predictive model because you can run these things on the computer, which does not cost money, but also you can get information you cannot get from the experiments. So a lot of predictive models and are needed here. So that combines, the temperature history and predicting microstructure, predicting the mechanical properties. Also, we want to know how the part will perform after we build the parts, and based on all this other information. We also work on the new applications, such as making new alloys, composite, multi-materials, functional gradient and layered materials, building new types of ladder structures, and also repair and manufacturing. The list goes on and on. I just listed some sample examples of applications we work on this one. And also there could be some process monitoring and control, because you really want to ensure that your processes are going acceptably. So therefore, you have to do in-process monitoring of temperature, defect, any compositional change in all these things. These are very, very challenging tasks. So if you are particularly interested in doing, say, data analytics and feedback control, this could be a good way of getting engaged in working on those aspects. That will eventually, these are very vital components for industrial implementation of additive manufacturing. So I have mentioned this one to you. So what we want to do is that we want to go from the process, okay, machines, and then we want to link it to the microstructure. Okay, so these are different microstructure images. You see that one. Eventually, what we want to do is that we want to predict the mechanical properties. At the end of that, hey, what people are interested in is actually performance of the parts. So you need to know what kind of mechanical properties that you need to have. So linking these three will be very, very important, okay, for the future of metal additive manufacturing. Without having this type of linking, you have to do a lot of trials and errors. And academia is a wonderful place to get involved in something like this one, so that you can actually help people in industry and in implementing this additive manufacturing in the most more cost efficient way. Okay, so this is kind of a roadmap that we have created for a long time. And so basically what we want to do is that we want to develop this type of integrated process models. And I call them enabling tools for rapid process optimization and qualification, right? So you have to qualify the parts that you are making. In order to do that, you need to have tools, right? And you cannot just visually inspect that one. You cannot do trial and errors. You have to have some tools. So what I'm saying is you need to have the components of the models. The links here, temperature history, geometry to the microstructure, and eventually in the mechanical property, thermal stresses, and all those things. Okay, so I'm going to spend a few minutes in describing some of these activities here. So this is a complex problem. Actually, if you are working in mechanical engineering, you probably get engaged in a lot of different things. So if you're thinking about actually physics, underlying physics of metal additive manufacturing, there are a lot of things going on. So I have color coded here in this what we call the physical flow diagram. So the red portion is basically thermal transport issue. How powders interact with the energy source, such as a laser, electron beam, how do they melt, how they evaporate, how they cool, and all those things. It's a complex physical problem. You have to understand that one. The second one, green boxes are when you actually liquid changes into solid. Basically, you start forming something called the microstructure, grains and grain boundaries, phases, and all these things. You have to be able to understand that one. So that's the part that is connected to the red portion. Then this microstructure will be later on related to stresses and strain and all these things. Also, it's affecting the properties as well as the final geometry. So these all different modules are actually interconnected. You want to study these things to be able to understand how the parameters that you use will affect the result of the property. And this requires a multi-scale modeling because things happen at different scales. So for example, if I want to study heat and mass transport in a molten pool, it's thermal fluid problem. We use a continuum approach for this one. So it's a macroscopic model. But if you're trying to predict the microstructure and grains and texture, things like that, it's more like a say micro scale. We're dealing with some models in the micron level. But if you're talking about the phases and composition, and you have to do the work at the atomistic level. So basically, you have to combine the macroscope scale model, the microscale model, and atomistic level work, and all basically based on the first principles. So that's why it requires a multi-scale modeling approach to tackle this type of problem. So I talked about this one. So we want to basically link these things using this multi-scale modeling approach. That's what we want to do. Okay, so I think it's the same diagram and as the previous one. So let me just go through this one and quickly here. So I think it's, I want to emphasize. So I just want to show what complexity of a model you have. So you don't have to now understand these equations because most of them you are undergraduates, so probably difficult to comprehend this one. But basically, this is what you learn in your heat transfer fluid mechanics class. It's what we call the hydrodynamic model. So basically, you consider all these things: mass conservation, momentum conservation, energy conservation, all these things. And you have to solve all these equations simultaneously to get the solution, because that's needed to capture the physical mechanism undertaking place. Not only that one, you have to understand that how actually powder actually interact with the material. So basically, what we want to do is that we want to start from all the input parameters, such as the laser shape, profile, powder feed rate, material property, incoming powder velocity, gas velocity, convection, and basically you want to do the whole 9 yards and to be able to calculate the temperature of field and considering those things. So, okay, so graphically what you see is it's how simulating the powder flow, and then after you actually do the yellow box simulation, you should be able to predict the fusion zone, heat affected zone, and actually track being deposited and all those things. That's what you want to do. And you do the same thing for the powder bed one, and something called, we use a discrete element method to study how the particles flow in the bed, and then rest of that one is very similar to this one. So basically you will see, and this the particles will drop on the surface there, and you see that how that we simulate the motions of each individual particle. After things get settled, we'll have the layer of particles deposited on the bed, and basically then you will start doing a simulation of this one. Okay, then roller will actually push these powders and spread them over the entire bed so you can get a uniform thickness of the powder, and that's what we do. And this is all done with the discrete element method. Then what you do is that you started simulating that basically interaction between the laser and the powder, and what you see on the left side is actually the temperature field in melting of the powder taking place. That's what you see now. Something like that is what we want to predict this. So this is actually a simulation result. My students have worked on this one for a long time. So what you see that during the powder bed process, and you can actually predict how the powders melt and how the temperature field is developed. So top view, side view, and front views are what you're seeing. And this type of modeling tools and provide great inside information that you cannot really get experimentally. So this is why modeling tools are very, very critical in actually understanding the physics correctly. The second portion you want to do is basically once you get the temperature field predicted, you want to predict the microstructure. So this is another image my students have created. So basically in this case, as a laser beam moves around, and let me see if I can play this video. And basically your grains, you have a melting and solidification, so grains get elongated and change the directions. And like I said, microstructure affects the resultant mechanical properties. So basically we need to predict what kind of microstructure you have. What you see on the left side is actually images that you get from the experimental results. So you see the grain boundaries and how the grains are sized and oriented. Those are the things that we want to get out of this certification model. And a lot of materials people study that one, and so do mechanical engineering. So that's the next component that I was talking about, that one. And then last part is that you want to predict the mechanical properties. So you have to consider detailed microstructure and porosity for predicting mechanical properties. In old days, you probably use a continuum element and you use something called the constitutive model to predict the mechanical properties. That's not sufficient. Today, you have to consider all the microstructural details because different microstructure will produce different mechanical properties. So then besides, you have to consider all the temperature history and resultant microstructure because it's a localized heating and cooling. Therefore, you have a very, say, inhomogeneous microstructure you will have. So a lot of people think of advantages additive manufacturing actually processes. They get excited about that one, but they don't understand difficulties and problems it actually contains, basically. So one of the problems that you will encounter is that microstructure you produce are heterogeneous, that they're not homogeneous because locally material is heated, cooled, and depending on how the laser beam is scanning the surface, that you'll have different heating, cooling curves everywhere. And so therefore, there is no way you get uniform microstructure. So you have to understand how these things are affecting the resultant mechanical properties. Some are good, some are bad. So basically, this is another portion of this one. So what we have been working on over a long time is that how we actually consider the microstructure details directly and to predict the mechanical properties. Okay, so if you know the microstructure, can you predict, say, yield strength and ultimate tensile strength, how material is going to be ductile, how it's going to behave under tension, compression, fatigue, and all those things. So, that's the type of model being developed. All these things could be a very good research topic for graduate students and for years. But, that's the type of work that you will see them. Another part that we have been working on is that basically predicting the residual stresses. So it's a thermally induced stress. And so you know that by the time you build the metal added parts, you don't see this much on the polymer parts because they are performed at the low temperature. And for metal parts, you'll get thermal stresses. So you can have a distortion or residual stresses left. So these things actually involve many different mechanisms. So I just here drew a kind of diagram that shows how the stresses are affected by temperature and the microstructure. And all these things are actually important ones. So they all affect each other like this one. And then you can actually do the prediction of residual stresses here. So after additive manufacturing is done, what you see on the left side is actually complex residual stress field and induced by additive manufacturing process, okay? That can affect your part performance, such as a fatigue life, distortion of that one. So you want to be able to control that one. So in order to control, you must understand. So when you predict this one, and you should get good residual stresses. So on the right-hand side is actually predicted residual stress versus a measured data. So you see several measurement data points are overlaid on top of the predicted values. So if you have a good physics-based model, you should be able to predict these things and to the accuracy needed enough to be able to use to qualify the parts. So this is what, see what we have been doing. The last portion here in the model, what you want to do is that you want to actually test the performance of parts in the virtual domain. So we have now learned how to actually control the process parameter to get the desired microstructure, desired mechanical properties. But these mechanical properties can be different than what you get out of a conventional process, like in machining or casting or extrusion, because the process is different. Microstructure, no matter what you do, are going to be different. So are they going to perform better or worse in the real situation? So basically what we need to have is this part level, it is a performance evaluator. So basically you combine all these things and we simulate the actual parts, whether that's engine or say you have landing gear, whatever components in the rockets or whatever things you actually simulate under thermal mechanical cycles and see if they perform well. So that would be the future topic. We have not gone there yet because we don't have good enough models that actually capture the entire physics. But we have come a long way, and there are so many people around the world working on this. So because this is the most important aspect in additive manufacturing for the future, and it's that one. Along with that one, I have to mention this one. Okay, all the things we have talked about are basically physics-based models. So we're engineers, some of you are scientists. So we like to have a physics-based models. But the thing is that one, they are computational, very intensive. It takes a long, long time to simulate those things there. So therefore, you want to also use alternative approach. And you have heard something like this, AI-based modeling, data-driven modeling. Because, people actually can say detect your signature, faces, a lot of things, different things. Google uses that one, and Amazon uses this one. Many other, I see, internet actually service providers are using this basically AI-based modeling approach. You actually want to capture the relationship between input and output without actually having without the need to identify exact physics of this one. Basically, if you have enough number of data, we should be able to capture that information. Once you capture this information in the data-driven model, you can make a decision very quickly, really real-time basis. You can actually tell it's right or wrong. So this is what's working behind the scene for almost everything that we are using these days. So these data-driven approaches have been is actually more popular. So we want to incorporate this type of, new domain into this physics world, because there are a lot of things actually you can do with the data-driven model. And, obviously, there are a lot of efforts being undertaken around the world, also as well as at Purdue. We have a big data science initiative here at Purdue going on. So now what we want to do is basically you want to close these things like this one. So you want to do all the multi-scale modeling, and you want to combine this one. You can also loop around this one with some of the data-driven approaches there, so that we can actually do the experiments, modeling, data-driven approaches together. And so we can one day basically quantify all the, the properties of all A and B, the parts, and quickly and accurately. What are the remaining research needs? And I think many people are interested in this one. So I gave a talk at the National Academy of Science a few years ago. So I actually extracted some of those things from a slide I shared at the time. So first thing is what I talked about: predictive models that can guide experiments, help rapid qualification, multi-physics, multi-scale modeling approach, data-driven approach. Also, we need to have improved experimental techniques. There are a lot of in-situ measurement techniques, such as X-ray synchrotron measurements and other types of novel measurement techniques that can actually provide a lot more information. So basically, if you like to work on the measurement side or instrumentation side, this is a wonderful application. You can actually get involved. So that way you can actually gain inside information and about the physics, but also you can actually use them to validate your predictive models, okay? There are a lot of property-related issues because basically it's a thermally driven process. And so there are a lot of properties we need to calculate these things correctly, such as optical, thermal, magnetic properties, and other things like that one. So we want to be able to measure or predict these properties. That's another huge area that people are working on. Also, this last one is very important. It's not, you know, it cannot understate the importance of this one, new materials and microstructural design. Okay, so people are constantly trying to come up with a new material that will give a better performance. Okay, so now we have ways of doing this one because a lot of computational tools you can use to explore different materials in atomic level, also in the lattice level. So you can actually do this type of discovery of new materials and microstructure by using predictive models. That's another area what we see. So let me talk about some of the facilities we have at Purdue. We have 3 direct energy deposition systems. So I have a list of people who own this equipment. Purdue has purchased 3 powder bed fusion systems, the Renasha AM400 systems. This is going to be shared equipment and anybody can have access to. So Purdue spent about $2 million to acquire these 3 machines. We also have purchased a binder jet printer, okay? And this is located at the BIDC, also share the facility, and you can actually, anybody can go there. One of my students is using this binder jet printer and to study the mechanical properties of the material built by the binder jet. And we also have a couple of faculty members in ME who are using other types of additive processes, cold spray in the Professor Martin June, ultrasonic AM Professor Gilbert, Professor Pipes in the materials, also has a lot of polymer AM machines. So if you are interested in polymeric material, he's the one of them, and you can actually contact to learn more about that one. We have numerous tabletop non-metallic material printers, and I have a few of them, but they are just all over the place. So if you want to do a non-metallic 3D printing, that one, we have something called the 3D printing club. You will join that one, you have access to these printers. You can print many different materials. I have several undergraduate students actually doing some printing of non-metallic materials through this Purdue 3D printing club, and they can print these things using different printers there. And also recently we have actually, in my lab, we have actually developed the capability of actually doing additive manufacturing in the solid state. It's called the friction stir additive manufacturing process. You don't melt the material, and you just basically plastically deform bond them, and that has some advantages for materials like aluminum. Okay, so by no means the list here is comprehensive here. I held the workshop about a year ago, and these are the people who participate in my workshop. And I brought about like a dozen different industrial companies. These are the people who actually spoke at the conference. So I know they are working on additive manufacturing, but there are probably many other faculty members who are working on additive manufacturing. Okay, so with that one, and I spent about 35 minutes talking about some of the research activities going on at Purdue. And I'll be happy to answer any questions you might have for the next 10 minutes or so.
Right. Thank you, Professor Youngchun. If anybody has any questions, I guess some of them posted. So Parth Bhalla, he posted, "Sir, is the research done by a group focused more on experimental work or analytical work?"
Actually, we do together. So, you know, if I talk about my activities personally, we do them together. it's my graduate students do both analytical work and experimental work. Depending on their focus, it could be 70-30 or 30-70, but someone's work can be more geared toward the experimental work. Another student may be more geared toward the experimental work, but mostly they work together because the greatest teacher of all is nature. So you cannot really do modeling work without understanding physics. So you have to watch the nature, the process, and learn from there to be able to capture the underlying physics. So they are not exclusive. We work together.
And then Mr. Moni Ruzaman had a question. If you could redirect him to some faculty with open positions in additive manufacturing.
Well, that is difficult for me to tell. I believe I received an email from him, right? I will try to get back to him. I had a very tight schedule whole day. So, I think what you can do is that you can probably come to Purdue site and look for people. And certainly I'll try to give my reply to you. But you are welcome to contact other people but I cannot really personally do the traffic control of that one. Okay.
Thank you. And then are there any specific softwares that prospective students should be aware of while using these experimental facilities?
Software we use is for mostly to do analytical work, not necessarily to do the experimental, related experimental facilities. But the things we use are such as like a Fluent and Abacus, COMSOL, MATLAB, but then other things are all in-house developed software. So you will have a mixture of, commercial software and in-house developed software. And of course, any faculty member will be interested in exploring any other software if the software provides certain capability. We also use a software for microstructure image analysis. It's called 3D, a 3D Dream, I guess. I'm not sure I got the name correctly, or ImageJ software, things like that, to analyze the images. But then there are a lot of other software we have to use related to the instruments, particular. But they are very specific to the instrument. Okay. Next question.
Anybody who would like to ask any questions? I think there was one more posted by Parth Bhalla. He
Okay.
wants to know if there are any openings in your group for either PhD or master's.
Yes, answer is yes, but it's all case by case. So if you are interested in working with me, probably the best way is contacting me by email. My email address is shin, very simple, shin at purdue.edu. So if you send an email to me, and then I will answer, I'll reply to you. Yeah, so yes, I have some open positions in the future.
Do we have any more questions?
So since there are no more questions, let me tell you why Purdue. Okay, so let me add a few, words to that one. So I know that there's a student who are graduating from many different schools. You have many different choices in terms of the graduate school. Number one, Purdue has a very good academic reputation. We're constantly ranked the top 10 in the country. So ranking 4, 5, it doesn't matter, and that's just a number. But top 10 means something. You're consistently ranked higher. The peers are actually valuing the education that we actually provide into the world very much. And also, second thing that I have noticed here, and working at Purdue for now, nearly for 3 decades, that we are very, say, application-oriented program, and particularly mechanical engineering. So if you see the laboratory facilities that we have in, say, MA, really, you will see it's unmatched. I visited almost every university in the country, and our lab facilities are really excellent, very well developed, because we have been working on application oriented. And basically, we're trying to say provide the best education to students, and they can go out to industry. And also, we have produced many students who have gone to academia as a professor. So it tells us something about the quality of the work that the program that we have here at Purdue. So, certainly, you have many choices. But one thing I can tell you, if you decide to come to Purdue, you'll never regret. Okay. Are there any questions?
Those are all the questions that were there in the chat.
Okay.
So thank you so much for answering.
Okay, good. Well, have a good day then.
Thank you very much.
Okay.
Thank you, everyone.